Okay guys, time for the third and final installment of limits at infinity. Let's go ahead and just jump right in. Let's try the limit as x approaches negative infinity of 4x minus 3 square root of, well, I actually copied that wrong, but like you'll know the difference. 2x squared plus 4x. That just makes the arithmetic a little bit more difficult, but we'll just sort of hang on to the radical. Now, remember, I'm approaching negative infinity right here. I have a first degree in the numerator. I functionally have a first degree in the denominator because it's a quadratic square rooted. I know that in order to multiply by the reciprocal of the highest power, I have to multiply by 1 over x, and then I have to multiply by its equivalent down here. But I have a problem, because like I said in the last video, you have to remember that the square root of x squared is equal to the absolute value of x. And if that's the case, for negative values, this is going to be negative and this is going to be positive. So that big ratio right there, the ratio right here in brackets, does not equal 1. It actually equals -1. So we have to plop a negative in there in order to ensure that we're multiplying by 1 and hence not changing the form. I mean, changing the form but not changing the value, okay? We can't change the value. This is the whole multiplicative identity property. So we need to distribute that, and we're going to get -4 plus 3 over x, and we get the square root of 2 plus 4 over x, and that winds up being -4 over root 2. And you can ask your teacher whether she cares about rationalizing the denominator, because actually once you get into calculus, that sort of starts falling out as something that we do as a general practice. Okay? Now, let's do another one. Limit as x approaches infinity of t to the 4/3 minus 9t to the 1/3, all of that over 8t to the 4th plus 2 to the 1/3. Okay? Now, what is the degree of the numerator? Well, it's very easy. It's t to the 4/3, right? So 4/3 is the highest power in the numerator, and therefore that's the degree of the numerator. What's the degree of the denominator? Well, it winds up being exactly the same thing, okay? Because what we have here is we have a 4th power, but the whole thing is cube rooted, right? Well, what you need to remember, and this one we don't actually have to do sort of the rigorous way, we can actually just sort of reason it out, right? Well, whatever it is that happens here, I know that this is basically 2t to the 4/3. Because as x goes to infinity, what happens is this value right here and this value right here stop mattering, okay? Because, sorry, that don't want to confuse anybody. Okay, as t goes to infinity, the t to the 4/3 right here and the 8t to the 4th right here, they start increasing. Now obviously that's increasing faster than a constant because a constant doesn't increase, so that 2 sort of stays put as 2. But that 9t to the 1/3, it's increasing. It's increasing slower than t to the 4/3, and so much slower that it stops mattering what goes on there. Okay, so really what we have in terms of this is we have we can actually sort of transform this into that and recognize that the limit is going to be 1/2. Okay? Now, Nah, I'm not going to get into it. Let's go ahead and do one that's a little bit different. Okay? Now, those of you who I met with on Skype have already seen this, but I thought it was neat enough to go ahead and bring it up here. Now, that is the limit as x approaches negative infinity of absolute value of x plus x over x plus 1. And some of you are thinking, my gosh, I hate absolute value. Well, I've explained this to you guys before. Absolute value is actually very, very simple. The problem is because there's not a whole lot of conceptual richness to absolute value, we don't spend a whole lot of time on it, okay? We basically gloss over it. We hit it a couple of times per year when it actually winds up being, relevant to the particular discussion. But because we don't sit there and dwell on it, ad nauseum, we wind up just not being conversant with it. We're not used to it. But it's really not all that hard. If you remember, let's go ahead and just do an example. The absolute value of 4 is, yes, right, 4. Absolute value of negative 4 is 4, okay? Now, what are the absolute value bars doing here? Now, I'm not looking for the definition. We all know the absolute value is distance from 0, okay? It measures the magnitude of a number, or magnitude of a value, rather than its direction, right? The positive or negative tells you which direction up the number line. That tells you how far, okay? So it measures the magnitude without respect to the positiveness or negativeness of a particular number. But what work is it doing right here? And the answer is, this is doing nothing. It's not doing anything. Absolute value of 4. Well, 4 is already positive. Just let it, slide on past. It becomes 4. Now, what functional work are the absolute value bars doing here? You're like, well, it changes a negative to a positive. Okay, I see that. What I mean is, how else do you change a negative to a positive? Well, you multiply by negative 1. Okay, well, that's the functional work that's going on here. You multiply by negative 1. Okay? If it's negative. If it's positive, you do nothing. If it's negative, you multiply by negative 1. Okay, well, that was numerically. Let's go ahead and apply that here. So if I'm plugging in increasingly large negative numbers, then for our purposes here, absolute value of x is synonymous with negative x, which means that this winds up being the limit as x approaches negative infinity of 0 over x plus 1. That's not hard to figure out that that's 0. Okay, well, let's ask a quick question. What if absolute value of x plus x over x plus 1 was evaluated as x goes to positive infinity? Well, remember, if it's negative, the functional work that it's doing is it's multiplying by a negative. So absolute value of x becomes negative x. But if we're actually going with positive numbers, it actually doesn't do anything. So all you really have to do is just take those absolute value bars away. It winds up being x plus x, or 2x over x plus 1, and that limit is 2. Okay? Now, let's go ahead and move on to a couple more. I want to hit a couple of more high points before we move on to the limit definition of a derivative, everybody's favorite, especially after you've actually seen how to take a derivative the short way. So the limit as x approaches infinity of the square root of x squared minus 1, all of that over 2x minus 1. Okay? Now, what is the degree of the denominator? It's 1. What's the degree of the numerator? It's 1. That is a quadratic square rooted. So I know that I'm going to multiply by the same thing. I just have to frame it a little bit differently for the denominator as I do the numerator. Now those two, this denominator and this numerator, are equivalent as long as I'm taking positive x values, okay? As long as I'm plugging in positive x values, the absolute value of x is equal to this x, and therefore this quantity right here is equivalent to 1. I have not changed the value of my expression. I am merely changing the form, and therefore I can go ahead and multiply that across, and I wind up getting 1 minus 1 over x squared underneath the radical, and I wind up getting 2 minus 1 over x. Okay, this right here and this right here fit my theorem. Now, I didn't restate the theorem in this particular lecture, but remember it from lecture 2 on limits at infinity, and therefore I get the square root of 1 over 2, or 1/2. Okay? Now, there are some limits at infinity where I will not be able to make recourse to my theorem because they are not polynomial in nature. So what happens if I ask, what is the limit as x approaches infinity of cosine 1 over x? Well, here we just have to kind of reason it out, okay? As x goes to infinity, what happens to 1 over x? Well, 1 over x goes to 0, okay? So, I mean, you could actually do a substitution and say, oh, let's go ahead and let y equal to 1 over x. And so this transforms, this transforms the limit into the limit as y approaches 0 of cosine of y. And if that helps you, if that makes you, feel all warm and fuzzy inside, that's fine. But you just have to know that as x goes to infinity, 1 over x goes to 0, and cosine of 0 is 1. Okay? Now, a couple more before we sort of finish up here and move on. How about the limit as x goes to infinity of x minus cosine x, all of that over x? Okay, well, the first thing that I'm thinking about is, okay, well, that's a monomial denominator. Is it possible to separate those fractions and make this a little bit easier for myself? And the answer, of course, is yes. So what I'm going to wind up with is 1 minus cosine x over x, right? Because when I separate the fraction, I get x over x minus cosine x over x, and the x over x just reduces to 1. Okay? Now what happens as x goes to infinity of cosine? Well, as x goes off to infinity, cosine just keeps oscillating back and forth between 1 and negative 1. 1, negative 1, 1, negative 1, 1, negative 1, 1, negative 1. It never gets any larger than 1. It never gets any smaller than negative 1. And of course, as x goes to infinity, that 1 to negative 1 oscillation in the numerator starts to be absolutely minuscule compared to how gigantic that denominator is getting. So functionally, as this happens, cosine x might as well be a constant, right? So, remember the theorem. It's the limit as x approaches infinity of 1 over x to the n is equal to 0. And of course, we change that to k, any constant, right? Well, for our purposes, cosine x might as well be a constant because it's getting no larger than 1. It's getting no smaller than negative 1. So, I mean, it's not going to do any more damage on this x to the n in the denominator as, say, like a 17 would or something like that. Okay, so basically we just have to reason that cosine x is just as innocuous and harmless as a k, any constant would be. And so this actually winds up fitting in a loose sort of way, and I wind up getting 1, right? Because this right here goes to 0, and the only thing left is this 1 sitting out in front of it. Now, how about the limit as x approaches infinity of sine x over x? Well, we remember sine x over x when we were dealing with those trig limits, those of you who are BC. And you know the limit as x approaches 0 of sine x over x is 1, right? That's sort of an identity. And, you know, I even had sort of that optional video where I proved it using the squeeze theorem. But what happens to sine x over x as x goes to infinity? Okay? Well, you have to remember that the same thing roughly occurs as happens with cosine x over x as it goes off to infinity. And you can't, it's a relatively simple one, but I want to underscore the fact that we went over combination functions. And I actually emphasize combination functions a bit more than most people do because I emphasize graphing and transformations more. And remember that basically once you understand transformations, combination functions wind up sort of piggybacking on that and sort of being an extension of the same logic, okay? So if we want to deal with the y is equal to sine x over x, isn't that just 1 over x times sine x? Isn't that the same thing? Well, 1 over x, if it were a number, if it were a coefficient, it would just be the vertical stretch or the vertical shrink, right? But as x goes to infinity, that's a shrink that becomes shrinkier, okay? Basically, when x is equal to 2, it's a shrink of 1/2. When x is equal to 100, it's a shrink of 1/100th. When it's equal to 1 million, it's a shrink of 1/1,000,000th. So this winds up being sort of a variable vertical shrink, so to speak, okay? And therefore, like I said, it's a shrink that as x goes to infinity, gets shrinkier and actually winds up shrinking as it approaches 0, okay? Now, that was a couple more examples, including a couple that were not polynomial based, and therefore we kind of had to use our reason more than just straight up method and procedure. I'm hoping that that actually helps flesh out sort of the whole phenomenon in terms of limits at infinity. If you guys have any questions, please, like I said before, shoot me an email, comment on the blog, do whatever it is you need to do to get a hold of me, and I will, of course, supplement as needed. Those of you who were a part of the Skype sessions, I enjoyed our time together. Those of you who are not, I look forward to next time, and I will wish you luck on your test coming up this week. Be on the lookout for some more videos as I will post them, hopefully in a timely fashion so that you can see them, review them, and absorb them before your test. Bye.